So hello again, everyone, and welcome to 3DOptix live session. In today's live session, we are going to cover two use cases. One is basic illumination, and the other one is Kohler illumination. The two use cases are already can be found on the 3DOptix website under resources and use cases. And in each and every use case, there is a PDF that you can download and an OPT file that you can upload to your software and can play with the same design. Keep in mind that most of the feature that Keith is going to demo today, specifically around the configuration of light sources, and specifically around the advanced simulation analysis capabilities, are available for our premium users. They are not available for our free user. As a free user, you'll be able to upload the design, see it, but you will not be able to do all the modification and the advanced analysis. So without further ado, Keith, the floor is yours, and you can start. We cannot hear you, Keith.
There we go. How about now?
Perfect.
Perfect.
Go ahead.
Okay. Well, thanks, Gail. Hello, everyone, and welcome to another 3DOptix live webinar. My name is Keith Myers, and I'm an optical designer working with 3DOptix. So today we're going to overview some applications in illumination that include basic methods and a more specific use case, Kohler illumination, using the 3DOptix web-based platform. So generating good illumination is very important for imaging applications, and there's many ways to achieve a desired spatial profile at the imaging plane. The ability to analyze how a light source is affected by an optical system will help prevent bad designs from being chosen. So we're able to conduct a lot of this analysis in the 3DOptix environment, and hopefully this will help us determine the best path forward for our systems. Okay, so with that said, I hope you enjoy the webinar. Let's go ahead and jump into the design. I will share my screen. There we go. Okay, now we are in the 3D layout. So the first thing we're going to do is review the current light sources that we're going to use for this webinar. We're going to right-click so we can add our light sources. And the two light sources we're going to be adding are plane wave and point source light sources. The plane wave sources are great for simulating lasers and other collimated sources. And the point source is great for simulating LEDs or trying to discreetly build up a extended source, such as a tungsten lamp or a large LED. Okay, so we'll go ahead and click on Add Light Source here. We'll add a little light source object to our outline. So once we click on it, we'll go up here. First thing we're going to do is add a laser source. So this will be our laser source here. So we'll rename it laser source. We'll also put it at the origin so we know where it is. There we go. Then we're going to change the light source settings. So for the source type, the default setting is plane wave. We'll keep that as is. For the appearance, we'll change this to red, just so we'll be able to track the light source individually, easily see it in the 3D layout. 3D layout raise, we can do up to 200, so we'll go ahead and put 200 in there. Fletch raise, because this is going to be pointing down the optical axis, we don't really need this, but this is a nice little feature in case you have a complicated optical system to see which way the rays are actually incident and facing. Okay. Spatial information, we're just going to have a circular beam that's 5 millimeters in diameter. We want this pointing down the optical axis, so we'll keep the angular information 0. Wavelength, so we'll go ahead and edit that and choose 520 nanometers. And for the spectrum type, just user defined. There's a lot of other options here that are very useful if you're trying to simulate different types of sources. Power, we'll keep that at 1 watt. Because this is a laser, we'll go ahead and have it polarized. We're going to have a linear polarization, and the orientation angle will be 0. Now, you can also increase or decrease the polarization ratio or the extinction ratio. Either one of these boxes will change the other. So if we change the polarization ratio to 1000, we get 30 dB. It goes back, and again, the same thing, changing the extinction ratio will change the polarization ratio. Okay. So there's our first light source. Now we're going to add the point source light source. So we'll do the same thing, add light source, click on it. We're going to name this LED source. We'll move this slightly above the laser source here. And we'll go into light source settings. We're going to choose point source this time. For the ray colors, we'll have these as blue. So with the point source, because they can be quite small and hard to see, we have the choice, we have the option to change the material color, opacity, and radius. For the radius, we can make it larger so it's easier to see where it is. And also the material color, if it's somewhere in the optical system, that's hard to see. And change that to a brownish color. Let's make that a little bit more red. There we go. So that's a nice little feature there, just to make it easier to visually see. So again, we can increase the 3D layout rays to a maximum of 200. I'll actually move the radius down just a little bit for this application. Again, Fletch rays not needed right here. For the spatial information, we'll keep it circular. Angular information, we'll keep that part the same. However, we're going to change the divergence of the source. So we'll do a 5 by 5 degree diverging beam. And for the wavelengths, so for this, because it is an LED, we're going to assume that it has some spectral, some relatively broadband spectral output. So we're just going to do a simple top output, and we will do 450 nanometers to 550 nanometers with 10 nanometer step sizes. And this will auto-populate our wavelength list here. We can also change the weight if we want to, but we'll just keep it very simple for this. Go ahead and hit apply. Okay, now our light source is set up here, and we'll keep the polarization power just the default settings. All right, great. So let's go ahead and propagate the simulation, and then we can see how our sources are outputting. So while this is coming up, we definitely want to check out our light sources before we implement them into our optical system. It's always a good idea to look at the raw output so you know what to expect, and it'll also help you drive your optical requirements or optical component requirements as you're designing the system itself. Let's go ahead and stop here. Looks like the computer is a little bit asleep. Let's try that again. Okay, let's try that one more time. Perfect, there we go. Okay, so here is our optical output. Now, because I changed the color of the rays here, we need to go up here and change the ray color palette to user defined. Perfect, now that'll bring up the color palette that I've chosen. Okay, let's go ahead and add a detector in front of each output. Rename these LED detector. And the other one, a laser detector. So we'll do 100. We'll put it 100 millimeters along the z-axis, give it a little distance. We'll make the output a little, or the detector half widths a little bit smaller. There we go. That should cover that. Go ahead and click on that detector again, and we'll just duplicate it, bring it down to our laser. Laser. Make sure that we've got it relatively in place. There we go. So right along the same axis as the other detector. Okay, great. There we go. All right, so let's go up to the analysis portal and let's take a look at our sources. First thing we want to do is change to advanced spot incoherent irradiance so we can get a good profile. And we'll look at, and we'll use 200 by 200 pixels. We'll do the same thing for the other detector. We'll just make them the same. All right, we will run analysis, and then we'll have a look at our beams and see what they look like about 100 millimeters from the source point. All right, so just talk a little bit about the output that we will see. Both of these sources will have a top hat output, so there will be a very flat top spatial profile, so we don't have to worry about any intensity issues on them. Perfect. Okay, so here is our LED detector, and here is our laser detector. And again, as you can see, they're very, very flat intensity-wise over the spot size. Obviously, the LED is diverging, so it'll get larger as it moves away, and the laser is collimated. It's collimated output, so it'll stay the same. All right, so now we know what our optical outputs of the beam spatially look like. Okay, great. So one other item I want to go over for the point source, so we'll go back to light source settings, is we have some divergence here. And we have 200 layout rays. Now, if we have a very divergent source, say something on the order of 80 degrees, we propagate the simulation again, you'll see rays spread out, but because we're only tracing 200, it'll look like none are actually hitting the detector. However, if we run the analysis again for the LED detector, you'll see that there is a lot of intensity, a lot of rays hitting that detector. So this is just because we're visually limited to 200 rays, and we should be able to see more on the output. Now the output's a little bit sparse. If we were to increase the light source rays, a couple orders of magnitude, and rerun this, we would see more rays hit the detector. So something to look out for when we're building up sources, make sure you're tracing the appropriate amount of rays. And if you don't need to spread your light source out as much, definitely kind of hone it down to only or just output into the optical system that you'll be using. You won't have to trace as many rays, and then you can use less rays and it'll be faster. Okay. So with that, choosing the angular divergence, we also have a couple different options for this. We can use the half cone angle elliptical far field, half width rectangular far field, or the half width at Z. So the half width at Z just says along the optical axis in Z direction, at this distance, you'll have this waist size. So there's a couple different ways to use our point sources, which is very handy depending on how we want to model our light source and how our light source actually acts. Okay, great. So the next thing I want to do, turn off the light source here. So I also want to look at how the light sources are polarized as they make their way through the optical system. This could be important for any polarization selective surfaces or polarization sensitive surfaces. We want to make sure that we have the correct polarization incident on it. Also, if we're trying to use such concepts as Brewster's angle, we can do that and check and make sure that we're doing the right thing with our light source. So we're going to take the laser light source. We're going to duplicate this. We're going to bring this down a little bit. We're going to do polarization source 1. Okay. Bring this down, minus 100 and 0. Okay. And under light source, we've got plane wave. Not going to worry about the appearance because these will be polarized in different directions, so we'll be able to tell which is which from that. Okay, so this is oriented at 0 degrees. Now I do want the spatial information, the radius to be a little bit smaller. So we'll do 1 millimeter there. Okay, and we'll duplicate this just so I have another source that is polarized in the opposite direction, or the perpendicular direction, as it were. Okay. Down here, orientation angle 90 instead of 0 this time. This way we have two polarized sources that are polarized perpendicularly to each other, and we can use the analysis features to actually look at that polarization state. Okay. Now we have polarization source 2. The last thing I want to do is come up here and angle it slightly so that we can propagate it through an optical system and see the difference. See it land at a different location on the detector. Okay, and to finish this off, we're going to go up the product catalog, and we're just going to grab a 25 millimeter lens. We'll use the public catalog because I only want to use lenses from companies, not ones that I've made myself. Go down here to lens, 25 millimeters. All right, perfect. So we'll just grab one of the smaller, little stronger lenses. So 25 millimeter diameter, 50 millimeter focal length, that's going to be perfect. Let's go ahead and add it to the design. There we go. So move this into position. We'll do 10 millimeters there. Okay. Then we're just going to simply duplicate this and move it into place. No need to name these or do anything else. We just want to see what the output of the light is. And finally, we're going to add a detector over here. We'll keep that size. Okay. Great. Now we'll be able to look at the output of our two polarized sources. So let's go ahead, go up here. We're going to turn off the laser and the LED source. We're just going to propagate the polarization sources 1 and 2. Go ahead and propagate the simulation. Make sure that'll make its way through the optical system. And again, this is very useful if you have some kind of polarization selective surfaces or using Brewster's angle, just to confirm that as it propagates through, you know what your polarization output is from either transmission reflection or at the image plane, illumination plane. So we'll go up to analysis portal. We'll turn off the LED detector. We'll turn off the laser detector. We only want to look at let's rename this polarization detector. Yeah. So we only want to look at the polarization detector. And we want to look at the polarized output. So we're going to go down here and use spot, incoherent irradiance polarized. And then we don't really care about the pixels. We just want to see the output on the detector. So we'll keep these just as they are. Okay, now once we run analysis, we'll be able to analyze the polarization states that are hitting this detector. Perfect. All right, we'll click on the analysis window, and this will pop it out into its own window. Okay, so we can see the X polarization component is here in the center, and then the Y is here on the left side. So that corresponds to the two beams that we have coming in here. All right, great. So we can actually see this physically on the detector in the 3D layout, and we can look at it on the detector. Again, this is, or in the analysis window. This is very useful if we do want to make sure that the polarization states that are propagating through and making it to an illumination plane are correct for what we think our application should be doing. Okay, so another good feature here is we can do polarization component none, so we can see both of them, or X and Y, as we just showed. So let's go ahead and do none. We can also do this map view if we choose one of the components. So we'll go ahead and click on that map view. And this will kind of give you a grid target pattern, showing you generally where it is, giving you a good rough estimate of distances. And we can make it medium or large density. And this kind of gives us a good idea of where our beam is, and easily kind of count how many spots different, or how many spots distant it is from the other beam. So looks like it's here, this beam. And if we go to the Y component, You can see it's about 2 spaces over. So if we take total number of spaces divided by the total area, kind of get a good idea of how far it is. The other thing we can do is in measure mode, if we turn off map view and go to none, we can actually measure, there we go, we can measure the distance here between those 2 spots. And that's very useful as well if we just want a quick and dirty analysis of how far to intensity patterns, to spots are, to laser beams are in our analysis window. And obviously from this dropdown, we can choose a couple of different measurement options. Because we're just looking at the 2 polarization states here, we just want to know the distance between them at this point. Okay, great. Let's go ahead and close that up. So the next thing we're going to do, now that we're familiar with the light sources and some ways to analyze them, we're going to look at point source illumination. So now we're going to look at reflected light off of a flat surface and observe the illumination. We'll have a few ways to interact with circuit properties for scattering and reflection. And this is a great way to customize your optical system to your specific setup. So what we're going to do, we're going to go back to our LED source, and we're going to make a few changes. The first thing we're going to do is go to my catalog, my private catalog. We're going to go down and we're going to grab this illumination surface. Pull that back a little bit, okay? And we are going to position this illumination surface perfect in front of the LED. That down a little bit. Great. That X will be, where do we want this? Right around there. Okay.
Keith, there is one question from the audience. Does changing the radius of the light source have any effect other than making it more visible?
That's a great question. And the answer is no. This is the appearance tab here is purely the appearance. So we can make this basically invisible. We can make it completely transparent. We can make it as big as we want with a radius. This is all just for the 3D viewer to help you kind of see what's going on in your optical system. It does not have any direct effect on any of the optical properties of the light source itself. All right, great question, great question. Okay, so let's get back to our illumination pane. No. All right, excellent. So that is a good spot for our illumination pane. And now we need to take the detector. And what we're going to do is we're going to move it over here. And we're going to look at that reflected light. So we will click on the detector. There we go. And we're going to first, we want to face the detector towards that illumination plate. Now, 3DOptix has a nice little feature here. You can see B on the back on the detector here. That means that's the back of the detector. We flip it over, we can see there's an F for front. Now, these detectors will only detect the light that is incident on the front of the detector. So we need to flip this around. And then I want to get a 20-degree tilt between the, a 20-degree angular tilt between the plane of the illumination plate and both the detector and the source. So we'll do that really quick. I want to do minus, it's 200. All right, there we go, perfect. And again, you can see the F on the front here. We know that's correctly positioned. Light source, going to do the same thing. I'm going to tilt it 20 degrees. Excellent. All right, so we will propagate the simulation. Now we're going to turn on just the LED source, turn off the polarization sources. So we're just tracing one thing at a time. Hit the propagation simulation. And just make sure that we've aligned our optical system correctly. Perfect, looks like it's good. The last thing we're going to do with the detector, we're going to make this a little bit bigger. I want to make sure that we can capture all the light that's coming off the illumination plate. Okay, good. So let's click on the illumination plate. And let's go to optical surfaces. Now, if you look in this window here, you can see that if you scroll over the faces, it'll tell you what face, or it actually highlight the face that you're looking at. Faces 1 through 4 are the edges or the sides. Faces 5 is the back, and face 6 is the front. So we want to interact with the front face, and we want to change some properties here. You can change the colors. We won't mess with that here. And also change the coding property. So right now it's ideal reflector. We could also do an ideal or a total absorber. And if we propagate simulation again, all this light will just be absorbed by that front face here. Perfect. Okay, let's go back to the optical settings. Go to phase 6. I'm going to change that back to ideal reflector. We are going to enable scattering off this surface because we want to do some scatter analysis and illumination analysis. So the transmittance, we want 0. We'll pretend this is a piece of aluminum or other piece of reflected metal, and the reflectance will be 90%. So that's aluminum, and you're losing about 10% to absorption. For a number of scattered rays, we'll keep that at 10. So if you want a lot of scatter rays, you can increase that. Relative power threshold, if you're not too concerned about low power rays, you can change this as well. And it'll change the illumination profile that you see to only important rays with enough energy that you want to analyze. So the first scattering model, we're going to do Lambertian. This doesn't have any options because it's equal scattering everywhere. So let's go ahead and look at what this appears on the analysis window. Okay, so we'll go back up to the analysis portal, and we will turn off the polarization detector, and we're going to turn on the LED detector. We're also going to lower the number of rays out so this traces a little bit faster. Okay. Also increase the number of pixels because we have a bigger detector. Want to make sure we can see the pattern. Let's go ahead and run the analysis. And as soon as this is done, we'll see a reflection and scattering off of the illumination plate. We'll be able to take a look at that and see what the illumination pattern is at this point. This detector can be an eye, it can be a camera, any kind of imaging detector that sees kind of the reflected light from the illumination plate. Let's go ahead and stop that and see if we can get the analysis going here. So another way to conduct analysis, if you're worried about stray light or light getting to components where you do not want it to be, is we can use a multitude of detectors in an analysis at different angles to see kind of where the light is going. And again, if there's a light sensitive component that needs to be isolated, we can look at that with a detector at maybe a different angle and see where it's going to get a good idea of how reflections and other scattered light and stray light affect our system. Okay, so that is a lot of light everywhere and can't really see what's going on. So the first thing we're going to do is we're going to go up here to change color palette, and we're going to do directional ray colors. This will help slightly in seeing what is going on with the rays, and we could also fletch them at this point to see which way they're going. This is all just kind of visual to help us see where the light is going in our optical system. Okay, let's look at the analysis portal here. So we have a bunch of light here, a light profile from the Lambertian scattering. All right, that looks pretty good. Depending on how we want to analyze our system, maybe we go a little bit further, change the scattering, add some optics in here, whatever we need. But this will give us a good basis on what the illumination profile looks like at this point. So really quick, we're going to change the scattering profile here so we can see what happens. We're going to change this, again, phase 6, which is the front, to a Gaussian model. And we're going to do a very small scattering angle here. Go ahead and save that. Let's run the analysis again and see how that changes that profile. It'll change it quite drastically because we picked a very small angle. Run the analysis. So obviously the detector is losing a little bit of light. So if this was my optical system, I would make the detector larger. And with the detector, so we change the pixels here and then the number of rays from the light source here in the analysis window. We want to make sure that that makes sense. So if you have 6,000 by 6,000 pixels, X and Y, then we want to make sure that we have enough light to illuminate each pixel. Because if we have too many pixels and every pixel is only illuminated by or hit by one ray, that will not give us the true profile. So a lot of the times I look at what camera or photo detector or whatever I'm using, and I will model that detector using the pixels. So we can tell 3DOptix how large the focal plane array is or the detector material is, and then how many pixels are in each dimension. So a really good way to properly, there we go. Let's try that. Okay. So it's a really good way to look at this as an actual system versus kind of a theoretical system. Yeah, knowing your specifications of your optical system, even the detector and camera materials will really help you get a good handle on how your optical system is acting. Okay. So as you can see, the scattering angle is 2 degrees on the Gaussian scattering. So we get a different profile here. So if we go back and do 5, we'll get a larger scattering profile. So let's go ahead and save that and run this again and just simply look at how the output is changing. Okay. And if we look at this, we see that the pattern is getting a little bit bigger here. So again, the Gaussian and Lambertian scattering is very useful to properly model your light source and also the scattering surface or illuminating surface that you're looking at. So there's a lot of parameters we can vary to uniquely customize our light source and optical system and reflecting surfaces. Okay. So we've gone over some basic applications and also the light sources that are available here. Let's go ahead and turn off the light. So now we're going to go into a more specific application or use case, Kohler illumination. So Kohler illumination is a type of illumination that uses parallel ray bundles at the illumination plane or target plane to illuminate the object or whatever you're looking at. Now that helps to even out the illumination because you're not re-imaging your source onto the object that you're looking at. So if you have an LED, we all know LEDs are very inhomogeneous spatially. So as you go off axis from the center point of the LED, it gets dimmer and that can affect your imaging ability for your optical system. So we are going to simulate a Kohler illumination system. First thing I'm going to do is add a few light sources. And these light sources we're actually going to use as a quasi ray trace. So this is going to be center trace 1. We're going to use these as kind of individual rays so we can see how they propagate through the system. Let's move this up a little bit. Great. It's going to be a plane wave. And we just want a single 3D layout ray. We're going to make this a little bit smaller. So this simulates a thin singular ray propagating. Let's see, I'm sure that there it is. Okay, perfect. It's very small right now, so it's hard to see, but luckily we have this pattern that goes back to the center of the breadboard showing us where it is. The appearance, go with a yellow. And we don't really care about the wavelength or the power of the polarization. Again, we're just going to use this as a quasi ray trace. So we'll go ahead and we're going to duplicate this. I'll name this center ray trace 2. And we'll put it at the same position. This time we want to angle it maybe 5 degrees. We'll go back to the center trace 1. We'll do minus 10 degrees. So this is going to simulate or start to simulate an extended source. So we'll have a couple different source points on here. And what we're trying to simulate overall is a QTH bulb that has some kind of length, and we'll put an appropriate amount of source points on there so we can look at generally what the illumination profile will be at the end. Okay, so I do want to duplicate this. And the only thing we're going to change, so we'll move this up 12 millimeters. So our source, total source size, the length will be 24 millimeters. So the center ray trace of the source will be here at 0, and then 12 millimeters up will be the top ray trace source. That, we'll duplicate that again because we do want another one. Make this top. Top trace 1 or 2. There we go. Top trace 1, top trace 2. Perfect. So for the top trace, this will make a bit more sense once I propagate the simulation. For the top trace, we're going to put a lens here. And with that lens, what we want to do is the top trace, we want to hit the top of the lens. And for source 1 of the top trace, we want to hit the top of the lens. And for the second source of the top trace, we want to hit the bottom of the lens. Again, this is a quasi ray tracing, so we can just align our system roughly. Okay, so let's go ahead and open the product catalog and add in that lens really quick. I have a couple lenses that I've predetermined I want to use. The first lens we're going to add is the collector lens. So this is going to collect the light from the source. And this is going to be from 3DOptix. Here it is, 110218E. Perfect. Let's go ahead and add that to the design. Now I want to put this, we'll rename this collector lens. Now what I want to do is put this one focal length away from the light source, just as a starter point. So obviously, as we evolve the system, the position will be optimized and changed. And that's all we really have to do to get this going here. Let's see, 800, 100, okay. Okay. So now that we have the first lens in here, we want to align the ray trace rays or the trace rays to this lens so we can start with the optical system. Kind of get everything in rough alignment, and then we can optimize later on. So for this, I think I do want to turn off the LED source, and that'll help us trace a little bit faster. So I do want the trace rays, the center and the top trace rays. Go ahead and propagate the simulation. Perfect. Okay. Now these center trace 1. Want to make sure everything is in the proper place. Okay, so there's different angles here that I put in. And then top trace 1 is 812 with a 10-degree tilt, and top trace 2 has a 0-degree tilt. All right, perfect. So what we want to do is we want to look at center trace ray 1. This is minus 10 degrees. So that's clearly a little bit too much. So we're going to change that to my predetermined 6.7. We also want to change trace 2 to be positive of that number. So hopefully this will hit the top and the bottom of the lens. Perfect. Okay. So what we're looking at here, in fact, let's go ahead and change ray color palette to user-defined colors. And we're going to change the center so we can more easily see what's going on. Go. Do the same thing to the other center. So you do have to click on the color that you want, or at least move the shift around, and then click somewhere in the box for it to change. Okay, so that is much easier to view here. So we can see our center trace, it's the top of the lens, and then our top trace rays are hitting the edges of the lens as well. I apologize, all the rays are hitting the edges of the lens because that's where the extents are, and that's how we'll figure out how we propagate it through the system using these trace rays that are going to hit the edge of this collector lens. So it looks like the top trace is not quite there. So let's try 13. And let's re-propagate the simulation. And now all the rays should be hitting the extents of the lens, and we can continue to add our optical system here. Okay, perfect. So that looks pretty good. So the next thing we're going to do is add or open the product catalog, and then we're going to add another lens. And this is going to be the condenser or the field lens. Here we go. So 110-0502 right here. So this is a little bit larger, 50.8 millimeters and 75 millimeter focal length. We'll add that to the design. We move it over here. Going to be the field lens. Okay. Then we're going to flip this around. We want the curved portion facing our image space. We'll put it in place. And let's put this 200 millimeters away. Perfect. We will propagate the simulation again, allowing the rays to trace through so we can get a rough alignment of the Kohler illumination system. And again, the purpose of this is to get parallel ray bundles at the illumination point. Okay, so as you can see, there's an intermediate focus here for this field angle or for this source point, and then a intermediate focus here for this source point. So let's pull this back a little so we can get those more lined up vertically. Let's go back to 180. Trace the rays. Okay, so a little bit closer. Let's move it one more time. Great. Let's see how that looks. And the hope is that the image points, there we go. So the intermediate image points here are a little bit closer. That's pretty good. Let's go ahead and move on now that these are relatively in position. And we're going to get one more lens here. Again, I have lenses that I want to use for this application, so we'll just copy and paste. All right, so 504E is another 50 millimeter by 50 millimeter focal length lens, and it's a double convex this time. This is going to be the condenser lens. So this is what's going to bring the light to the illumination plane. Let's see if Google can help me out with this. There we go. Okay. Move this in line. And then we're going to start at 240, get a little bit farther, or maybe 200. Let's start there. Actually, what we do want is this lens past that intermediate focus point or intermediate image area. So let's go to 240. Great. Let's go to propagate the simulation, look at how our trace rays are making their way through the system and see where they end up. Okay, so that is a little bit too close. As you can see, the sources diverging. Now, what we want from our Kohler system, Kohler illumination systems, we want each field or source point to be collimated as it's coming towards the image plane. So these are both diverging, so we need to move this lens a little bit farther away. So let's go to 60. See how our trace rays come out. Okay, that's a little bit better. They're still diverging a bit, but they're much better. Let's move it one more time. And this should be a relatively good rough estimation of where our optics should be in the system. Okay, perfect. That actually looks pretty good. So as you can see right here, in between these, there should be some pretty even illumination because all the rays are coming in, or all the source points are coming in collimated. So there's no focusing, and there should be even illumination in the space everywhere where these overlap, where the ray bundles overlap from the source points. So again, we have a source point in the center and a source point at the edge of the source, propagating through our optical system. And then we can see it right here where we have these parallel ray bundles where we should get a good even illumination profile. Now, critical illumination, where you actually image the source onto the illumination plane, that would be something like this, where we have a focal plane or imaging plane right here. If we were to stick a detector here, we would be imaging the source. So if the source isn't completely homogeneous and the intensity flat across the spatial profile, it would be a little bit harder to use this because you're going to have variations in the intensity at the illumination plane, and it will probably make it a little harder for you to observe your object if there's small features you're looking at. Okay, so let's go ahead and add a detector here. And we are just going to kind of eyeball where the detector goes. So this looks like a good area here where the ray packets converge and overlap. Forward detector. Okay. Put this along the optical axis. So we're at 325. Let's just do that. Make an even number. Okay. This will do 20 by 20. That should be sufficient. Okay. So now that we know the system is roughly aligned and this looks like a good position to analyze, what we're going to do now is we're going to replace the trace rays with actual sources. So we'll add another source here. So we'll do center extended source. This will simulate a source point in the center of our QTH bulb or whatever light source, extended source that we're simulating this. So go 800 in the center. Okay. Now we do want to use a point source. This we want to change the colors so we can see what the colors look like at the end. That circular ray pattern. And then we want to match, we've got the half cone elliptical far field. We want to match what we specified for our trace rays. So that was 13.22. This will allow our source to completely fill the lens. Okay. And then for wavelength, we do want 400 to 600 nanometers in 10 nanometer steps. So we want to simulate a white light LED, so a broadband source. So again, top hat, just a very simple simulation of the LED. We'll go ahead and apply once the wavelengths are populated. And we'll keep the wattage a little bit lower because we're simulating source points, not the full source. We'll keep it unpolarized because it's an LED. Okay, there is the first one. We will duplicate this 2 more times and we'll do a top and a bottom source point. Again, our extended source is 24 millimeters in length. So we're going to do plus or minus 12 millimeters around that center point. There we go. We're going to change the appearance again. It will do a green, somewhere around there. Okay. Then we're going to duplicate one more time, and this will be the bottom source. Okay, so 800 is 782, 8. Okay, so these are our 3 source points. We want to see how this propagates through and what the illumination is at that Kohler illumination point here, where they're all parallel and incident at the same place crossing. Okay, let's go ahead. We will turn off our trace rays, and we're just going to use the 3 extended source points here. So what we want to see is the light propagate through and then come down here to a waste area. Okay, so one issue here is we have these sources and we don't have any baffling here. So the source is going beyond lens 1 to lens 2 or the field lens. So the last thing we want to do here is put an aperture in there so we can block that light. Now this would normally be done with baffling and light blocks in the mechanical enclosure. But we just want to simulate that light block here. So what we're going to do is go to mask. And this is going to be our light block. We're going to upload an image. So I've created this image already in PowerPoint. It is a 4-inch or 101.6 millimeter square with a 25.4 or 1-inch hole in the center. And this is going to cover lens 1 or the collector lens. 50.8 is the half diameter of the entire image, not the center part. Let's go ahead and save that. Great. Okay, so we're going to put this right over lens 1, the collector lens. Okay, and this is going to block all that light from going through. We only want the light to propagate through that hits lens 1. Okay, let's go up here to view. Looks like, yeah, user defined colors. I forgot to change the third light. So let's go ahead and do that really quick. Here we go. Perfect. Now we've got 3 colors there so we can see which is which. All right, propagate the simulation one more time. And now we should have a good flow of the light through the optical system. Okay, that looks pretty good. It's much more clear where the internal focus is, or the intermediate image point, and where the Kohler illumination is going to happen. So it's going to really be at kind of the waist area over here where they're all converging equally. All right, so now we want to open up the analysis window, and we want to look at what that illumination pattern looks like. So we'll turn off the LED detector. We'll just use the Kohler detector. Spot incoherent irradiance again, because we're using the LED. We do want a few more pixels here, just so we get a good idea of what the illumination pattern is. Let's see, where did we put this detector? The detector is currently at 325. So let's get it a little bit closer here. I think it may be maybe 315. See what that looks like there. Okay, so we'll let that run, and then we want to look at the illumination evenness at that illumination plane here. And again, the purpose is to make sure that the illumination is very even so we can get a good picture of or an image of the object that we're looking at. Okay, not bad for a first run. So as you can see, it's definitely not overlapping perfectly with the 3 sources. So let's go ahead and move that a bit closer. Run the analysis. Okay, that looks a little bit better. Let's move it one more time. Let's move it to 40. Okay, so you can see there's a lot of overlap of the light, and it looks fairly even in the illumination. The last thing we're going to do is we're going to adjust the color map range. So we want to kind of see what even looks like. So we're going to specify that we only want energy over 0.04 to show up. All right, great. So that means there's only a couple spots that have high intensity. Let's change that one more time to 0.3. Okay. We change it to 0.2. Then we get more of an even illumination profile. So this is a good start. We could definitely move the detector and the optics around to increase the homogeneity of this illumination profile and get a very even illumination at the target plane. Now this is a good start, and we would want to optimize further from here. I'd also like to point out that because we are using refractive optics, there will be some chromatic aberration here, so you'll see a halo effect here. By using an all-reflective system, if you can get the same Kohler illumination, then you would rid yourself of chromatic aberration. So it looks like I'm out of time, so we'll stop there. So I just want to thank everybody for joining us, navigating and getting familiar with the web-based platform and the application we reviewed today, Illumination. So I hope you enjoyed what you saw, and this kind of helped you understand the platform a little bit better. This design file is available in the application papers, Basic Illumination and Kohler Illumination, so you can look for that on the website. And with that, I'll hand it back to Gil. Thank you.
Okay, so thank you very much, Keith. Stay with us. And we have another question. Is there any way to simulate an imperfect light source more like an actual LED? Do you want to take this, or do you want me to answer this?
Yeah,
Keith?
I can take that. So is there a way to simulate an imperfect light source more like an actual LED? So it's a bit more complicated. In most software packages, if you have a light source that doesn't have any symmetry, you're going to have to use different multitude of light sources to simulate that. Generally, with an LED, we assume it's asymmetric or symmetric about the optical axis. Now, if you did have an LED that had some hot spots and cold spots, you can definitely simulate that with a few light sources and possibly even some lenses or a mirror to get the output that you really want. So it's a little bit more complicated if you don't have that symmetry, but it's definitely possible. And the good thing is you get instant feedback from this, so you can see every time you make a movement, what's happening to the output of your light source.
I would also like to add that we are going to add pretty soon is several weeks, the ability to upload a ray file in the format of IES-25. And then you can get from the vendor the LED actual ray file, the measured one, and you can upload them to 3DOptix, and you can simulate that. So that will be available in several weeks from today.
Hey, Gil, I think there's one more question that I can take here. So it was asked, is there a particular reason why you eyeballed these distances instead of using the precise focal lengths of the lenses? Yes, so I didn't want to really get into the weeds of exactly where to put these lenses. There are obviously equations that you can use to position everything perfectly. What I really wanted to put out here is if you had an unknown system or you really wanted to optimize something for your application, just how to do that, kind of showing step-by-step using some quasi-trace rays, moving the lenses back and forth and looking at it on the analysis window. So that's why I kind of eyeballed everything. I wanted to show kind of the versatility of using the application, but you can definitely position these perfectly. A couple things we didn't go over is changing local coordinate systems on the lenses and other objects for exact positioning between surfaces, even using the thickness of a lens in your separation between two elements. So there's a lot more you can do here to get it specifically exactly where you want to position your optics and objects.
There was a question that was sent to us earlier about reflective optics, relay lenses, and condenser in and this user has an ultra broadband light source and would like to know about about it. So I don't know if you mentioned this.
Yeah, so Kohler illumination is a technique to get even illumination at the target plane, object plane, image plane. So if you are able to use reflective optics or mirrors and other things like that, then you would be able to get rid of chromatic aberrations that'll happen. Now it'll introduce itself as a halo effect at the illumination plane when you're using a broadband source and lenses and other refractive optics. But again, if you can achieve the same parallel ray bundles using off-axis parabolas, concave, convex mirrors, flat mirrors, then you would be able to get rid of the chromatic aberration.
Okay. So thank you very much, Keith. And just again, would like to mention that this recording will be available on our website probably next week. You'll get an email about that. As I mentioned earlier, most of the features that Keith showed are advanced feature and are under our premium license. You can try them out. You have 14 days free trial if you put your credit card, and you can cancel any day without getting the bill. We process the payment after 14 days. So if there aren't any questions, so thank you very much for attending. And we will probably attend again in about 2 to 3 weeks with another live session. Thank you very much and have a great day. Bye-bye.